So now we welcome everyone. We open this section. And I'm Pohan Lee from Shida Pudong. And let us introduce yourself and Shuri first.
Hi guys, my name is Huan Gu from National Taiwan University, SAP.
Welcome.
杨佳慧 from Fongjia University.
Okay, every team introduce your team member. Reporter first.
Yes, team we go.阿什么燕瑞、徐明文、林秉成、曾义鼎、张维谦。
Welcome.
Captain of the Lifelong Doji. My name is TYPT. This is Shu Yirui. This is Li Chenggang. This is He Yi. This is Xu Weichen.
We are Team Excelsior and we are from Concordia Middle School. I am Stanley Chen and this is I am Chen Xiaochen. This is He Ziwei. This is Li Yiding. This is Liu Xingyu. This is Qiu Jiazhi.
Okay, welcome. So the opponent challenges the reporter for the problem. Which one?
We challenge problem 11, spring hysteresis.
Reject.
Reject. So challenge again.
We challenge problem 15, whaling bulb.
We accept.
Okay, great. So everything you can write down your name on the blackboard. So for the reporter, you have 5 minutes to presentation. So please well prepare yourself. you have 12 minutes.
Good morning, honorable judges and fellow opponents. I'm the reporter from Team Waco Go Go. The problem I'm going to present today is number 15, whaling bowl. So this is the problem statement. When you strike the side of the metal bowl containing some water, you can hear a characteristic sound. The sound changes when the water in the bowl is moving. So later on, I'll explain and investigate the phenomenon, focusing on relevant parameters and the frequency spectrum analysis. Okay, so you can see that we put the bowl on a shaker, and the bowl would let out a wailing sound, and there is uneven water distribution. Also, you can see that water flows in the bowl, and we're going to investigate that. How do they affect the frequency? Okay, so let's move on to our theoretical model. A shaker, like in our phenomenon, moves in a circular trajectory, where there exists an orbital acceleration that acts as a centrifugal force. That can be shown as equation 1, where this r denotes the radius for some water mass. The centrifugal force causes the water both to start flowing and change its geometry, shifting the frequencies of the bowl. On a shaker, the water surface is not a perfect parabol. It's like this, because the shaker's middle is probably like here. Higher rotational speed or more water enhance the geometric modification, which leads to a wider frequency shift. Now, if I want to look at this problem, this phenomenon in a mathematical way, I use the finite element method to write the matrix of mass and stiffness as this equation, where x of t is written in this way, where this u is the vector that denotes the shape of the wave, and this term is the oscillation. And next. So after some derivations, we obtain equation 3. Oh, and we can see that this omega f, where is the frequency squared, is the eigenvalue that related to the natural frequency. And u, like I have mentioned before, decides the mode shape and affect the sound quality. So this equation shows that the change in mass distribution has an effect on both the frequency or the sound quality. Okay, so the frequency after considering water distribution can be written as this. And if we assume that water has negligible impact on the stiffness of the bowl, increasing the mass of the material leads to the decrease of the frequency, as shown in equation 5. So now we define natural frequency as the frequency an object naturally vibrates when not driven by a force. Later on, we perform qualitative analysis on how the natural frequency shifts depending on relevant parameters. And there are these kind of shifting rates. Okay. So let me introduce our experimental setup. We use this SG90 motor to propel this tuning fork hammer to avoid any unwanted sounds. Also, we dangle the bowl by tape on this metal rack on a shaker. Okay, next page. We prepare LMS size 304 stainless bowls with the same shape and side base ratio to ensure that they have the same shape, and to further examine our theory. Okay, the hammer consistently beats the right bottom of the bowl. We also make sure that before the experiment starts, the bowl's tilt be no larger than 0.3 degrees to ensure accuracy. Okay, so this is the spectrum we're going to be using a lot later on. A spectrum is a dB frequency graph which demonstrates the accumulation of frequencies and dominant peaks for us to compare. In the following experiment, we'll record about 15-20 hits and show the peaks that exceeds roughly minus 48 dB. This is the largest relative detectable dB. So let's move on to experiment 1 about rotation. We change the rotational frequency of the orbital shaker and observe the change of frequency on each spectral line. Okay, so we change the rotational frequency from 0 RPM and increase by 25. So as you can see, for S size 100 grams, S size bowl, 100 grams water, you can see that every spectral line increases as the RPM increases. And the same phenomenon can be observed in both the M size and the L size bowls. However, you can notice that I drew 8 spectral lines in the S size and only 5. And that actually implies that larger bowls does not have higher peaks that exceeds minus 48 dB. Okay, so in short conclusion, we find out that the higher the rotational speed, the higher frequency each spectral line will be. Also, in addition, smaller bowls exhibit more spectral lines with higher frequency. So let's move on to the next experiment about the mass of water. We change the mass of water and observe the respective frequencies on the spectrum using this formula that we have talked about before. So we're changing water mass from 50 grams to 100 grams, and we're comparing them under different scenarios. Okay, so if I use this frequency, if I use this equation, I can use the 50 grams to get the theoretical 100 grams, and I would compare it with the real 100 grams. Okay, so you can see this might not be that close, but later on, when it's rotating, the theoretical line and the real line are very close. And this is the same for M bowls 0 RPM, M bowl 125 RPM, L bowl 0 RPM, and L bowl 125 RPM. So in conclusion, we find out that the more water mass, the lower the frequency each spectral line will be in every condition that we have tested. Additionally, increased water mass does not seem to have a significant impact on K, the stiffness of the bowl, due to the close fit of the theoretical and experimental data. And this actually fits our assumption. So now let's move on to experiment 3, about bowl size. We observe how the bowl size influences the ratio of the frequency of different spectral lines to that of the first line. And here, I want to make sure that you understand that the ratio of n equals the frequency of the nth spectral line divided by the frequency of the first spectral line. So again, we are changing different scenarios. So if we recall experiment 2, we can see that the ratio between the water mass is fixed. So that makes the 50 grams to 100 grams ratio all the same. However, see things that starts to deviate. When we compare L and M and S size, we can find out that the L size ratio is the highest and M is about middle and S is a little bit smaller. And the same thing can be observed in 100 grams. And we know that from the previous graphs. So in a short conclusion, we found that while water mass does not have much impact, larger bowls show higher frequency ratio, which implies a more discrete peak distribution. Okay, so let's move on to our analysis. We observed that the bowl lets out a wailing sound when it's struck. So by changing the rotational speed, we investigate the phenomenon through analyzing the patterns on the spectrum. Okay, so we're again changing the rotational speed and different bowl size to compare. So let's just see these 3 graphs. This is 0 RPM, 75 RPM, and 125 RPM. We find out that as the rotational speed increases, apart from shifting rightwards that I have mentioned in experiment 1, the most dominant frequency peaks right, which I have bracketed in this gray one. So if I want to analyze this phenomenon, I use an approximated triangle with a base of A and height of B. So if the ratio of A to B goes up, then actually means the peak widened. So we observed that within the data range we collected, the ratio between the base and height of the approximated triangle adhere to an empirical formula that we derived after observation and trial and error. So as you can see, for S size 50 grams whaling bowl, the data can be written into this equation. And later on, I would like to compare the alpha value and beta value. Okay, so this is 100 grams groups. Let's move on. This is the M size 50 grams. Okay, M size 100 grams. L size 50 grams. And L size 100 grams. So as you can see more easily, the higher the rotational speed, the larger AB ratio will be. However, we find out that the more water mass, the larger A and B alpha and beta gets, which implies the wider peak. And that is possibly caused by the wobbling frequency of the bowl. And here I mean the adjacent frequency from the original frequency. So in conclusion, from the equation, we know that the change in mass distribution has an effect on both the frequency of the sound quality. Okay, so the faster the shaker rotates, the higher each frequency spectrum gets. The more water mass there is in the bowl, the lower frequency spectrum line gets. So in the data range, mass does not have much effect on the stiffness of the ball, which is K. And it adheres to this formula. So, and after some observations, we observed that the square of angular velocity and the ratio of the approximate triangle of each peak, only the first peak, adhere to the empirical equation, this one. So in conclusion, the faster the ball rotates, or the greater the water mass, the more conspicuous whaling will be. Okay, and also the larger the ball, the higher the frequency ratio the spectrum line gets. Now let's talk about some possible deviations. Although it's ran by a machine, the spectrum line still exhibits some inconsistencies, probably due to the background interferences. For example, the noise caused by the machine or the wind sound. So therefore, we will compare the background spectrum and the experimental spectrum to eliminate the unwanted peaks. And now let's consider the Doppler effect. Because it's rotating, so the frequency difference between moving toward and away is approximately 0.098 Hertz, which can be neglected in this sense. And also, although it's ran by a machine, there could still be fluctuations on the contact position. It's not always in the right middle. So that may lead to inconsistent mode. It might be like 1, 0, like 0, 2. So therefore, we lengthen each recording to about 2 minutes to extract the best peaks. And in future research, we aim to investigate how different texture or position of the contact area will impact the experimental result. These are references, and thank you for listening.
Okay, 2 minutes for moment.
What is the most significant source of the sound generated by the ball?
Because I put
Showing some please.
I put the cell phone right beside the ball, so it's the loudest.
And what is the significant source of the sound generated?
I think it's the clanging of the sound, clanging of the ball.
Thank you. And will the frequency of the sound generated remain constant throughout a single strike?
I don't think so.
Okay. Is the damping effect of water the main reason for the change in sound? Damping effect.
I think so.
Okay, thank you.
That's them.
Which kind of water movements do you generate?
I put the ball on a shaker, so it's a rotation.
Okay.
It's an orbital.
Thank you.
Orbital shaker.
Is the wave excited in the ball a standing wave or a traveling wave in your experiments?
Can you what is a chocolate wave?
Like standing wave and traveling wave, which one do you think is excited in your experiments?
Because the water is moving, so I cannot say that. So
Okay, thank you. Does the movement of water alter the duration of the sound? The time that the sound keeps occurring, does the water's movement affect it?
I think so.
Okay. Does the contact area between the ball and the supporting surface affect the frequency?
Yeah, I think so.
Thank you. Will the material and the size of the ball make a difference in characteristic of the whaling sound?
I do think so.
Do you record the vibration patterns of the ball with high frame rate camera? The vibration patterns.
No, I don't use camera.
Thank
I
you.
only use recording.
Does the vibration mode differ with different directions of the wave?
I did not observe the wave and the water is moving, so I cannot really tell you the answer.
Thank you. Does the water's rotating rate affect the ball's vibration patterns? The rotating rate of the shaker.
Yeah, it does.
Hands up.
Thank you.
Thank you.
Okay, for 3 minutes for observation.
the opponents would like to skip the time.
Okay. So opponent take the floor, maximum 4 minutes, and discuss with the group.
Honorable juries and fellow competitors, I'm the opponents from Team Xavier. Today, I'm going to oppose problem 15, welding ball. This is a problem statement. When you strike the side of a metal ball containing some water, you can hear a characteristic sound. The sound changes when the water in the ball is moving. Explain and investigate the phenomenon. And we will mainly focus on what is the mechanism behind the phenomenon and how relevant parameters affect the sound. Now, let's talk about the reporter's outline. The reporter mainly used the theory of the finite elements method to testing how different parameters affect the phenomenon of the sound, and of course, the frequency equation. About the experiments and analysis, the reporter has to different frequency ratio using the shaker to change the parameters, which is really precisely. And about the ball size, they have the 3 different sizes of the ball, which is L, M, and S. And of course, the mass of water is one of the influencing factors we need to consider. And about the rotation, which is our PN of the shaker, as the previous mentioned, they have done many experiments to minimize the deviation. And about the spectral analysis, they mainly use a spatial analysis to describe the phenomenon and the frequency of the sound. And about the error analysis, they have did the background interferences. How does that affect to our phenomenon? And the double effects to explain why might this affect. So this error analysis is completely, however, it needs still some quantitative proof to prove that to your quantify to your experiments. And of course, the damping effect is one of the influencing factors we think might create the deviation. Now let's talk about strong and weak points of the reporters. The reporter did a great job on a well phenomenon demonstration, and there is a lot of parameters discussed in the reports, and there is a clear demonstration of the experimental process. And about the weak points, the reporter didn't talk about the boundary condition of some parameters, which we will discuss in later. And there is lack of error bar in some cases, and some charts are not clear marks, and lack of experimental data of parameters. Now, let's talk about the points to be discussed. Firstly, we want to discuss the qualitative explanation. This includes the source of the sound. What is the most mechanism affect the sound generated by the ball? Which is we think it might be the vibration of the ball. So that's one of the main influencing factors we want to discuss later. And of course, the water movement. Since the problem statement mentioned only make the water move, we wonder why is the water critical to the experiment, and what if we change the different dimensions wave? For example, the circular, the y dimension wave. And of course, the water of the wave is important to the experiment and the effect on sound. About water volume in a ball, which is one of the influencing factors to the experiment. So we will discuss later. And about the damping effects, we will mainly talk about the vary with different frequency. About the second one as our parameters, which is the shape of the ball, and this includes the spheres and cylinders. And of course, how different striking position on the side of the balls affect the phenomenon. Third is the experiments and setup. For the setup, we want to discuss the contact area under the surface of the shaker, and the repeat consistency and different striking method. How does it influence to the experiment? Finally, move on to the data analysis. We want to discuss the boundary condition. This includes the size, materials of the ball, and of course, the water manual previously mentioned. About deviation analysis, we want to discuss how to hold the ball will minimize the deviation. About the vibration pattern, we'll discuss how different direction of the damping affect the phenomenon. About the water rotating rates, it's one of the influencing factors we will discuss later. About the frequency amplitude, vary with time, and that's the thing we want to discuss. And I would like to invite the reporter to have the discussion.
Okay.
First question is, why is the moving water critical to the experiment?
Mike, can you go back to the first conclusion? So from this equation, we know that the changing water movement has an effect on this N matrix, which I say is the matrix of the water distribution.
So what if today the water is static? Will it have generate a wailing sound?
No, I don't think so, because what makes the wailing sound is the frequency change, and the frequency change comes from the change of this. So if this stays stable, the frequency should stay stable.
So based on this formula, we can know the wailing sound mainly comes from the movements of the water.
Yes.
And the opponent wonders, how does the reporter define wailing sound in your experiment?
Oh, can I use the board?
Yeah, sure.
So if we do this on a normal spectrum, it appears like this. But if we do some like analysis, it can be split into different waves, like this. And these are the strongest, which probably like here. Like it will be like the thickest. And when the ball starts to rotate and the water distribution starts to change, there will be a kind of like a thing like this.
So we can say the definition of the wailing sound is based on the charts you have provided. That's the way how you judge the wailing sound.
And this graph, if you put it back.
So wait a moment, you just had 10 minutes for this.
If you put this thing back to this kind of graph, you can observe that because this becomes wider, this widens. And that is why I'm like using the AP ratio, because I want to observe this phenomenon.
So by observing this phenomenon, we can define this as the wailing sound.
Yes.
Okay, can you please turn to page 10? Page 10 about the setup. Thank you. Page 10. The opponent wonders, how does the ball's button contact area with the shaker? Did you let it up or just put it on the top of the shaker?
I use like 4 pieces of tape to dangle it on the rack.
So does the button of the ball directly contact with the shaker?
No, it does not. It's like floating there.
Do you think the things you dangle by tape will influencing the damping of the wailing ball?
I think using the tape greatly influences the frequency of the ball, because I think using the tape, it tightens the structure and makes it probably the frequency higher.
So this dangle by tape will influencing our experiment data?
Yes, totally. But throughout the experiment, I used this as a controlled parameter. So I think
Control variable.
Yeah.
And is the influencing of that can be quantified? Yes. Is the influence of the tape can be quantified?
You mean described by numerical ways?
Yes.
I can't do that. Can you do that?
We think we can predict what might happen. Can you please predict what might happen if we didn't put the dangle by tap beside the wailing ball?
Ideally, we think that it should be probably floated by a magnet and like absolutely no contact. But we have to. If we use a tape, then probably the tape will vibrate with the ball, and that causes frequency shifts apart from the like.
So we think we have the same files of if the contact area with other things is too big, it might influencing the factor of wailing sound.
Yeah, totally agree.
Okay, thank you. And how does the damping effect vary on different frequencies that cause the wailing sound?
Okay, so when the ball starts to flow, like this is on shaker, right?
Yes.
And the ball's radius is actually larger than the shaker's radius. So the ramming point is probably not the lowest part of the water. It's about like it's always in the middle. So I think if you change the rotational speed of the water, its distribution change, and the faster the ball rotates, it goes like very high, and the water thickness at the ramming point will change. So I think that's a big issue.
Corresponding to the setup, the opponents wonder when we use high RPM of the shaker, will it affect the stable of the setup? Since the wailing ball is
so that's why I didn't use any RPM over 150, because there are 2 boundary conditions. First, the water just go out of the ball. Yeah. And the second is that the tape starts to the tape is not stable enough.
That's the boundary condition of the shaker.
Yeah.
Can you please refine the exact value of the RPM of the boundary condition?
I observed that about 160 75 to about 200, the tape starts to lag out, like leaking sound, and that is probably not precise because the tape is probably moving.
Okay, thank you. And since you use shaker as the circular wave of water, right?
Yes, yes.
And well, the phenomenon being affected by different kinds of water movements.
Yeah. So when we're investigating this phenomenon, we try to. I think there are two main ways. One is like you have said,
Like one dimension.
One dimension like this.
Yes.
And one is using a shaker.
And what is the main differences between the circular wave and the one dimension shaking method?
I think the fundamental parts is all the same because what affects the frequency is the mass distribution. But the main differences between them is how the mass distribution changes. Because
So-
one is circular, one is like this.
So the main factor will not be the distribution during the process of the water.
No, it's a main
depend-
factor.
Oh, so it depends on the mass of the water, or can you please clarify?
I mean that you can every kind of vibrational origin is very good, but the fundamental thing behind all these is the mass distribution. So different shakers or one-dimensional, like they just change the distributional modes.
So can we assume that if the frequency of shaking is the same, there will be no differences between those two methods? If the frequencies we can maintain the same?
I don't think you can say that because like one is like this, like and turns to this, and one is like this and turns to
Yes.
this. So I don't think you can say that they are the same. But I think they both let out a waving sound. That's what I'm sure.
Oh, so based on these two factors, we can observe this phenomenon.
Yeah.
Okay. Can you please turn to your page 16? Thank you. The opponents find out that there is one line that's climbed up and have a decay region, like compared to those difference. Can you please define what happened here?
I think the first reason can be an error in the experiment. And the second reason is that probably the fourth spectrum has some kind of properties that we don't yet know.
So this line indicates the times you have did the experiment.
Because this is the frequency, and actually
Yes.
each line is tested more like 3 times, but they show the same frequency. So I choose not to show the error bar because that's a frequency.
So do you mean once the line is aligns with the trend of climb up, we can ignore this here because of it might be just little deviation to the experiment?
I mean, this still goes up, but just not as conspicuous as other ones.
So it might be with a little deviation, like you have mentioned in the background noise. Is it so?
Yeah.
Thank you. And can you please turn to your page 26? Well, the opponents wonder how does the theoretical line of the 100 derive by?
Oh, I think I didn't say it much clearer before. I use this equation because we assume that water, different mass of water does not affect the stiffness, and different mass here I refer to the 100-gram water and 50-gram water. So I use this equation to derive that ratio, and I time the ratio to the frequency of empirical 50 grams data.
Okay, thank you. I get your point. Could you please turn to the page 43?
All right.
Well, the opponents wonders why is the experimental data for the initial condition slightly lower than the fitting line? Or is this the fitting line or the theory line?
There is no theory because I use this line as this. This is the fitted line.
Okay, can you please turn to page 50? How do you quantify this possible deviation, or you just can predict it? Can you quantify?
I can because background. Can you move to the next page? Like I think for a normal person.
Thank you.
Oh.
Opponent summarize the discussion.
Honorable juries and fellow competitors, and about the summary discussion, we have mainly talked about the differences of the different parameters. The first one is the movements of the ball on different conditions, which is one dimension and the circular movements. And the second one is angle by tap that influence the frequency of the ball. The influence of the tap can be quantified. However, the reporter has minimized the deviation of the setup. And high RPM may cause the setup unstable. The boundary condition of the angular velocity is about 175. However, it may not be very accurate since the reporter didn't really have for example, 174 what might happen. And the last one is there were some deviation, but they could more or less be ignored. And the reporter thinks that this one can be fully quantified to complete the reports to make it more accurate. And that's the end of the discussion summary. Thank you.
Okay. The question of reviewer to opponent and the reporter.
First, I would like to ask reporter, how did you strike a ball in your experiment?
I use a motor connected with the hammer.
And did you strike only one time for one experiment, or you strike frequently?
Yeah, I strike 15 to 20 times, and I use the accumulated graph to extract the best beats.
And did the frequency all different when you strike different times?
Can you say that?
When you strike the first strike or the second strike, well, the frequency all be set the same.
I don't think so, but after a long term, I think accumulated frequency will be the same, like the highest.
Okay, thank you. And how did you measure the A and the B in your spectrum?
Like A and B, oh, that's the end result formula. So I use this approximated triangle to use to test this ratio. And you can see that there is actually no extension. So I only see this angle.
But I ask you, how did you measure this?
I just like this.
Okay. I would like to ask opponent. Because you asked the reporter how did he define the welding sound, so I want to ask you, how did you define the welding sound?
Like the welding sound in a reference text had provided, it has a special characteristic sound rather than the normal striking sound. So we think the specific welding sound can be defined by the FFT analyzation, like the reporter has shown in his graph.
Okay, thank you. And what other water movement do you think that will change the frequency?
Like since the problem statement has mentioned to make the water move, so we think different moving method will influence the frequency. For example, when we discussed with the reporter, we have discussed one dimension and the circular movements. And the other thing we really wonder is how does this one dimension affect the frequency of the welding sound?
Okay, and what about don't move the ball, only move the water like stir or create surface waves?
So do you mean we didn't move the ball, we only make the water in the ball?
Yes.
We think it will be related to the striking method we use, since we only make the water in the balls move. So it will relate to the striking method.
And the last question is for both of you. Do you consider the wall thickness of the ball will affect the result?
Well, I think the wall thickness is one of the influencing factors that might affect the results.
And what about you?
I only knocked the bottom of the hip, so I think.
Okay, time
it's
is
a
up
control,
for
right?
preparation for reviewer. 2 minutes. give you the floor.
I'm the reviewer of technical assembling, and I'm going to review the problem 15 welding ball. This is the problem statement. When you strike the side of a metal ball containing some water, you can hear a characteristic sound. The sound changes when the water in the ball is moving. Explain and investigate this phenomenon. And the key point of this problem is the frequency and location of the water. This part is the overview of the reporter. And for the theory part, they present the interference to the frequency equation, and they use mass distribution to explain the result. And for the experiment part, they explain the experiment set of relevant parameters and graph clearly, but the lack of data parameters. Also, they discuss about the possible deviation. For the conclusion part, the more the water mass, the lower the frequency. The larger the ball, the higher the frequency, and the higher rotation speed make larger AB ratio. This part is a remark to the reporter. For the advantages, they display the theory and result clearly, and they present the experimental operation clearly. Also, they answer the question efficiently. This is our suggestion for the reporter. You could explain how the errors affect the difference between experiment and theory, and you didn't talk about the boundary condition. And this part is a remark to the opponent. For the advantages part, their questions is short and clear, and they discuss the error in the experiment. And for the suggestions, they spend too much time in a single issue, because that some important issue didn't be discussed. Also, they say that some deviations should not be ignored, but didn't have an example. And for the discussion between reporter and opponent, the first question is what happens if the graph goes up and down? And the reporter say that might be experiment error, and the opponent is accept the explain. And for the reviewer, I agree with the reporter, but I think there maybe have some reasons such as it's not linear or something else. And the next question is why the moving water is critical. And the reporter said that from a theory model formula, the mass distribution affects the frequency. And the opponent also accept the explain. And for the reviewer, I also agree with the reporter that mass distribution affect the frequency, but I think maybe because the water is moving, it has some kinetic energy, maybe that will affect the frequency. And the next question is how did you define a welding sound? The reporter answer is AB ratio, and the opponent accept this blend. And for the reviewer, I think the AB ratio is a good way to define a welding sound. And the next question is how important of angle of tape will influence the frequency. And the reporter said that it's unclear and cannot define. And the opponent also always accept the explain. And for the reviewer, we agree with the reporter, but you can try to contact the ball and the shaker use a different way, such as using glues. And where is the angle? Oh, thank you.
Okay. Concluding remark from reporter.
Okay, so in our previous discussion, we discussed why is the moving water critical. And our response was that the change in the water mass distribution will affect the frequency of the sound polish. Also, the opponent asked me about the experimental setup. Does the bowl contact the shaker? Because that's a very big issue. That can affect the frequency of the bowl. And I respond that the bowl doesn't contact with the shaker, but has a contact with the tape. And the use of the tape might affect the frequency, but that is control parameters that we use throughout the whole experiment. And ideally, we think we can levitate it with a magnet. And the opponent will ask how the changing rotational speed affect the setup. So we have two boundary conditions. First, the water might just like get out of the ball, and also the tape is not stable enough to hold the ball. Okay, so again, the next question that we discussed about is the effect of shaking method. The opponent gives out a very valuable suggestion about also conducting the experiment on 1D dimensional shaking. And again, I say that they all depend on the mass distribution. Okay, next. And thanks for a worthy discussion. Thank you.
And, question from Julie.
So for the reporter, so you measure the sound quality and determine how the parameter affect the sound quality. So can you define what sound quality is?
In my opinion, I think sound quality is the tone of the sound. I want to make this term clear, which is probably like the sound of this. This is what I define as sound quality, the tone of the sound.
So can you elaborate more?
Oh, so because
how
I use
the parameter affect the sound quality? How in your conclusion you mentioned that some parameter affect the sound quality. So can you elaborate that more? For your conclusion, previously in your reports.
I think if we use the same material, like the same stiffness, the sound quality will stay the same. And yeah, and the balls are all the same.
Okay.
So, can you explain the meaning of this finite model you used in your calculation?
Good.
Yes, this finite element.
So there
I
are
want to know whether you know this method.
so like the whaling ball is a very complicated system. So we try to analyze it through using these matrices to simplify the system's like motion. And this M includes both the ball's mass distribution and water's distribution. This K is the stiffness of like the elements, different elements.
Can you agree this theoretical model is more simple?
We are not really sure about this analyzed system. However, since this theoretical model method can define the different shape of the sound, and we can know the sound properties from the charts. So we think since the theoretical model method can have in the charts can show the differences under different kind of conditions, it can be used. However, we are not sure if this theoretical model is used to this problem.
And because the reporter used this theory to fit the experiment results successfully, so I think this theory it does make sense.
Okay. So for the opponents to investigate the phenomenon, do you think that it is necessary to do the measurement with and without the water in the ball? Do you think it is necessary?
We think it is, because to compare if the water really influences the wailing sound, we think it can be a further experiments we can do to compare with the water is when the water in the ball is static or ball without the waters. We think we can compare its differences while doing the experiments to further analyze the experiments.
the reporter. 8, 6, 6, 7, 6. Okay, for the opponent. 8, 6, 8, 7, 7. For the reviewer. 7, 5, 6, 6, 6. Okay, we finally set. Okay, we can make a 10 minutes break.